Take a look at this problem. Suppose R1 and R2 are the roots of this polynomial. Find A, R1 plus R2, and B, R1 times R2. This could be easily solved by factoring and simply plugging in the roots. However, what if you want a more general equation? Take any quadratic ax squared plus bx plus c. This can be rewritten into a factored form with the leading coefficient multiplied by x minus the roots. Multiplying this out and organizing the terms, we can match the coefficients of like terms. This gives us b equals negative a times the sum of the roots, and c equals a times the products of the roots. Rewriting this, we get Vieta's formulas. Let's use this on some problems. If alpha and beta are the roots of x squared plus 5x minus 3 equals 0, what is 1 over alpha plus 1 over beta? A good approach to many of these problems is to do some simple algebraic manipulation and then plug in Vieta's formulas. If we simplify this, we can see that it's just the sum of the roots over the product of the roots. Using Vieta's, we can see that our answer is 5/3. Let's try another problem. Let a and b be the roots of the equation x squared minus mx plus 2 equals 0. Suppose that a plus 1 over b and b plus 1 over a are the roots of the equation x squared minus bx plus q equals 0. What is q? Using Vieta's, we can see that q equals the product of the roots. Simplifying, we can get that this is equal to ab plus 1 squared over ab. Using Vieta's on the first quadratic, we see that ab is equal to 2, and finally plugging this in gives us our answer of 9/2. Now what about non-quadratic polynomials? There will be a lot of notation here, so I'll explain as best I can. We'll start with our polynomial in standard form, which will look like this. N represents the degree of the polynomial, so starting at x to the n, and gradually decreasing until the last term ensures you include all degrees of x. A sub n represents the coefficient of x to the nth power, as do the rest of the terms. Now, we can rewrite it in factored form by once again taking the leading coefficient and multiplying by x minus the roots. Multiplying this out is a little tricky since it has infinite terms, but let's just see what happens. Multiplying a sub n by every x term, you get a sub n times x to the n. Now let's include some roots. If you multiply a sub n, one of the roots, and the remaining n minus 1 x terms together, you get negative a sub n times r1 times x to the n minus 1. Doing this for every root gives you negative a sub n times the sum of all roots times x to the n minus 1. Now choose two roots and n minus 2 x's. You could do this for every possible pair of roots, which would give you a sub n times the sum of every pair of roots times x to the n minus 2. You may see where this is going. If you choose, say, I roots, you get a sub n times the sum of every possible combination of I roots times x to the n minus I, since that's how many x terms are left, and finally multiplied by negative 1 to the I to account for the fact that every root term is negative. For notation's sake, we'll rate these sums as s sub I, where I is how many terms are added at a time. We can use this to get our final expansion. Now, we just remembered that this is multiplied out factored form, which is equal to standard form. So we can match the coefficients again, and we start to see a pattern. For any coefficient with value I in the expanded form, it corresponds to the n minus ith coefficient in standard form. More generally, this means that s sub I is equal to negative 1 to the I times a sub n minus I over a sub n. Let's put this to use. Suppose p, q, and r are the roots of the polynomial t cubed minus 2t squared plus 3t minus 4. Find p plus 1 times q plus 1 times r plus 1. Multiplying it out, we see these sums appear again. Plugging in Vieta's formulas, we can find that the answer is 10. Now let's close it off with one last problem. For real values of a, b, c, and d, the equation x to the fourth plus ax cubed plus bx squared plus cx plus d equals 0 has 4 non-real roots. The product of two roots is 13 plus I, and the sum of the other two is 3 plus 4i. Find b. One noticeable part of this problem is that the roots involve imaginary numbers, but the coefficients of the equation are real values. This means that the roots have to multiply together to become real. This is only possible when they are conjugate pairs, or complex numbers with opposite signs between the terms. Let's name two of the roots x and y, and have x bar and y bar be their conjugates. Since the sum and product of the pairs mentioned are non-real, we know they cannot be conjugates. So let's say xy equals 13 plus I, and x bar plus y bar equals 3 plus 4i. We know that the conjugate of these equations are true, feel free to work this out yourself, which gives 4 equations to work with. The question asks for b. Using Vieta's formulas, you can find that b equals the sum of every pair of roots. Writing this in terms of our roots, we get an expression. We already know these, and for the remaining, we can simply do some factoring. Plugging in our values, we can evaluate to get a final answer of 51. Thanks for watching, and I hope you enjoyed the video. If you have any questions, feel free to ask in the comments.